In this video, we're going to look at example 2 of shear force and bending moment diagrams from page 15 of the course notes. You can see on the screen just now, I've taken the beam that we're given in example 2 and put it onto our whiteboard here. As before, we're going to draw a line to represent our beam for the shear force diagram. So I'm just going to draw a straight line across our screen just now to represent our beam. As before, this beam has points representing the locations on the beam as well. So while this line represents zero shear force, we have an end A and B corresponding to those points on our diagram on the left-hand side. Now, if we remember what happens when we consider a shear force diagram, we're going to start on the left-hand side and look at how the shear forces are being applied to our beam. So on the left-hand-most side of our diagram at point A, we have a force of 7.5 kilonewtons being applied in an upward direction. So, as in the previous example, we would start at point A and move upwards. I'll just a slightly better line here. Move upwards by a value of 7.5. This is a straight vertical line for 7.5 kilonewtons. Now, in the previous example, we were considering where there's only point forces applied. So if we were looking at point C in the previous example, there was no uniformly distributed load here. What we would have is a straight line going horizontally until we reach point C. But that isn't the case here. We can see in our diagram there is a UDL applied to the beam. And so what we're going to do now, in order to work out how this should appear in our shear force diagram, is to consider what is the shear force just left of point C and what is the shear force just right of point C. So let's indicate on our diagram here a point that's just to the left of point C here. So we're saying this is almost at point C, but just before the 6 kilonewton force. So if we call this here the shear force at C, shear force at C. So just to the left of C, what we have is we've got the 7.5 kilonewton force acting up the way, and then we've got a downward force that's equivalent to our UDL, which is 3 kilonewtons per meter, multiplied by the distance between A and C. That's a total of 3 meters. So what we have here is 7.5 minus 3 times 3, which is 9. So that gives us a negative shear force of 1.5 kilonewtons. So we know when we get to, and I'll just indicate where C is in our diagram here. This is where C is in the diagram here. So as we get to C, we should be at a force of negative 1.5. Right, that's going to be negative 1.5 in the diagram. Negative 1.5, that's our shear force, because due to the UDL, although we've come up 7.5, we've come down a total of 9, 3 kilonewtons per meter over 3 meters. And how we would draw that in our diagram is a straight line from the top of that line at A. So I'm going to draw this in freehand. This is a straight line in from 7.5 down to 1.5. But what happens is we get to see, what's happening here is a 6 kilonewton downward force is applied. So just, if we're now passing the point C, so I'll just indicate in our diagram up here, just as we're passing C, it's immediately as that force is applied just to the right hand side here, what's the force, shear force acting just right of C? So just right of C, we have our 7.5 kilonewtons acting up and our 3 times 3 acting down due to the UDL. But what we've also got here is another 6 kilonewton force acting in the negative direction. And that added up is going to give us negative 7.5 kilonewtons. So actually we'll have another point at C, which is here representing negative 7.5 kilonewtons. And again, it's a Because this is due to a point force, we're drawing a vertical line, this time in the downwards direction because the force is acting down the way. So that's how we represent what's happening at point C. Now the next point force doesn't occur till the end of the beam, and we take the same approach with that as we have with point C. So if I just erase that in our diagram, let's see what's happened just as we arrive at B, so just to the left of B. So I'm going to be a bit briefer with my notation here. I'll call this SF for shear force at B, and I'll say JL for just left. So just to the left of B, what do we have? We've got the 7.5 kilonewton force acting up the way. Then we've got a force due to the UDL. Now this time the UDL is applied, it's down the way, it's 3 kilonewtons per meter, and the distance, the whole beam now has been covered because we're considering point B, it's a distance of 4 meters. And we have the force due to C, a downward force being applied. We're not interested at the distance at which they're 3 times 4 minus 6. We're not interested in the distance applied because these aren't moments. This is just a sum of forces. And this adds up to minus 10.5. So our point at point B is going to be minus 10.5. And again, because the only thing that's happening is the UDL, we have a straight but diagonal line down from our point at the minus 7.5 at C down to minus 10.5 at B. And the last thing we need to consider for our shear force diagram is what happens at B just as we get to B. So we call this just right of B, but effectively this is at B because there's no more beam at this point. We've got 7.5 from the force at A. We've got the UDL force of minus 3 times 4. We've got minus 6, the force acting at C. And we've got plus 10.5, the force acting at B. Now you can probably guess here, if we're adding another 10.5 on, and the previous one was minus 10.5, yes, we are left with 0 kilonewtons as our remaining force. And so we draw a straight line back up from this point to the end of the beam. And this completes our shear force diagram. And just for comparison, I'll put on the diagram from the notes so you can see this drawn a bit better, not freehand as I've done here. So this is what our diagram would look at. We'd have direct forces moving along the line when vertically along the line when we have a shear force being applied at a point, but we've got this diagonal slope representing the UDL. And so that's how we find our shear force diagram in the example where we have both a UDL being applied across the beam and point forces being applied as well.